Hi everyone, welcome back to our channel. Today we are going to find the solution for this given problem number 23. The question asked is find the Norton's equivalent across xy. Okay, so this is very simple problem. So actually I already told. So the Norton's equivalent we need to find out is, so we consist of an a current source. The magnitude of this current source is ISC, and which is connected in parallel to a resistor where this is called as Norton, and we are connecting to an load resistor where this is called as load resistor RL. So we need to find out this Norton's equivalent circuit. Let us look it into the method. So first I need to find out ISC. So ISC is done, just load resistance is not given in the problem. So what I have to do is just short circuit it. Okay, so here, so I'm going to short circuit across x and y. This is 5 ohm. So now what I need to do is I have to short circuit x and y. So I have been short circuited x and y, and I need to find this current. So whenever you look into this problem, so this is connected between 1 and 0. Okay, so now I'm redrawing the network. I'm marking this as node 1, and I'm marking this as node 0. What is the element connected? 5 ohm. Now between 1 and y, or 1 on x, so this I'm taking x or y and 0. What are the elements connected between 1 and x? Okay, so this x, y, what are the elements connected? So 1 is nothing but we have an current source. Between 1 and 0, a current source is there of current of 10 ampere, and between 1 and X, I have one more branch which is nothing but 10 ohm. This reduction is very important. You can see here between 1 and 0, 5 ohm is there. Between 1 and X and Y are same now. So X and Y are same, and this is the short circuit current ISC. Okay, so this X, Y, 0 all are same, and this flows. Okay, this is ISC, and this is the current between 1 and 0, and 1 and x is 10 ohm. So now I need to find out this current. So this is the current ISC. So I can find current in any branch. Let's try to do it by method 1. So I can find current in any branch by using a method called as current division rule. So many problems are solved on current division rule in our channel. Just check out. So I will leave in the cart also. You can check out there. So I want the current in this branch. First you write down total current. So what is the total current? Total current is 10 ampere into. So in this branch I want the current. What is the branch in parallel to this branch, which is nothing but 10, brought into the opposite branch resistor which is connected in parallel. So what is the parallel branch, which is 25, which is nothing but 10 divided by the sum of resistors which are connected in parallel. So what are the resistors which are connected in parallel to the network, which is nothing but 10 plus 5. The way you apply this is very very important. So therefore we are going to get 100 divided by 50. Okay, so this will give you an current. Do it with the calculator. 6.66 amperes current. So this is the way of solving by method 1. Okay, so you can solve it by nodal also, but no need. Just see here. So this is which node? First node between 1 and 0. I am redrawing it for more clarification. So this is a 5 ohm resistor, and you can see here this is I'm going to a current source parallel to a resistor, which is a practical current source. I'm going to use source transformation technique between which nodes? First node and zeroth node. Okay, so this is first node, and this is zeroth node or X node or Y node. So now I'm using the source transformation. Whatever the branch resistance is there here in parallel, I will get it as in series, which is nothing but 10 ohm. And I can see the current is flowing downward direction. This automatically this will be a positive terminal and this will be a negative terminal. So since current is flowing in this direction, this will be positive, this will be negative. Therefore, V is equal to I into R. I is how much? 10. So 10 I. R is how much? 10. So this is equal to how many volts? 100 volts. What? How the current is flowing now? So this is the direction of ISC. So I'm trying to solve it by one more method, which is nothing but method 2. So how to write down the current? So current in any branch ISC is equal to, so current is flowing. What is the leaving polarity of the voltage? 100 volts minus 0 divided by the current is flowing. Okay, current flows in 5, and you can see here the current ISC flows in 5 and the same current also flows in 10. Then I can say these two are connected in series, divided by 10 plus 5, which is also as the same 100 divided by 15, that is equal to, you are going to get 6.6 amperes of current. That is the procedure of solving. So now successfully we find this ISC, and we need to find out the next one is R Nortons or R Thevenin. Okay, so for this I'm trying to apply, or you can apply for anything. If you apply for this will be more better. Okay, so here you can see here, so here we have been short circuited. So here we have a 5 ohm resistor and a current source is there. Current source is there, you have to deactivate, means you have to make it as open, and it is connected to an resistance of 10 ohm, and this is node X and this is node Y. So you have to remove the load resistor. So already load resistor is not given, it is removed, and looking from the removed load resistance, find out R Nortons. Okay, so now current will flow in X, same current will flow in 10, and same current also will flow in 5. I can say now these two are connected in series. Therefore, which is nothing but, so between X node and Y node the current is flowing, and I can say that since current is not divided, these two are connected in series. Therefore, which is nothing but 10 plus 5. Okay, so which is the value of R Nortons is equal to 15 ohms. Therefore, the equivalent circuit, we are going to have two answers. This is the first answer, and the second answer is this one. Okay, this is 1 and this is 2. Okay, just substitute I short circuit current, it carries a current of 6.66 amperes, and equivalent value it carries is only just 15 ohms. So successfully we had find the Norton's equivalent across the node X and Y, and load itself is not given in the problem, that's why directly substituted. Hope you are able to understand the problem. I repeat the problem, those are unable to catch the logic. So first initially we want to remove the load. So load itself is not given, remove the load and short circuit it. If you short circuit it, and this short circuit is present between 1 and 0. So between this is node 1 and this is node 0, identify the element. Between 1 and 0, 5 is there. Between 1 and 0, what is there? A current source 10 amperes and a resistance of 10 is there. So automatically I am using method 1 and I find the current by using current division rule. So some people may feel this is easy. Second, people may feel, why don't we apply source transformation? I applied source transformation to this loop. Automatically it has been converted into an voltage source, and I find the current I is equal to V by R. So V is how much current is leaving. What is the leaving polarity? Plus 100 divided by 10 plus 5. So next one, the same network I am taking. So the process of solving R Nortons is similar to that of an Thevenin's. So wherever you have current source, deactivate that current source and open circuited this. So already we have the load. Okay, it's not given in the problem. So load we have to remove. I remove the load and finding the resistance from the open circuit. So the current flows in 10 and current flows in 5 is same. I can say they are connected in series. So successfully I have been designed the Norton's equivalent across XY. If you feel my explanation is good, please like the video and share with your friends. And if you are watching the channel for the first time, if you have any doubts, let me know in the comment section. And if you're watching the channel for the first time, subscribe to my channel, which is KV Tulasi Ram. So kindly support this type of free channels for the development of student and faculty. Yours obediently, Ram. Will meet in the another video. Thank you for watching.